Aditya Godbole. I'm the CTO of Last9. Quick poll: how many of you are developers, like application developers? Okay, how many DevOps, Ops? Okay, anything else I missed? QA, and then that's it.
Full stack.
Sales? Acha, nahi. Primarily. Okay, cool. Uh, so what I'm going to cover today is we are going to go a bit under the hood of what happens in the shell when we run all these pipes, redirections, etc., and try to get an idea of how it works. So a bit of background as to why this is important is so when I was doing I was doing engineering, electronics engineering, and I didn't have a lot of clue about software, like especially in second year or third year, I think. And for my project, I wanted so it was a computer controlled house lighting system, and I wanted to do a client server kind of architecture where I send commands from the client and the server receives those commands and manipulates the electronics behind it. But back then, the only thing I knew was DOS, right? And that was the only thing that was actually available in our lab, like the blue turbo C screen, etc. So I had no idea how to do a client server, like how to do multitasking basically as a fundamental feature in the OS and do it programmatically. So I went to the college library. That was the alternative to Stack Overflow back then. And I had heard that Windows does multitasking. So I picked up a Windows programming book. First chapter was W handle something something, then more. The types just got larger and larger in their names. And by the time I had reached the 15th or 16th page, I got a temperature of 102 and I had to stop. Right? So then I said, okay, this is not something I can do. So then I went back to the library, I was scanning, and then I saw a book called UNIX Programming. Okay. I picked up the third or fourth page gave me exactly what I wanted. Right? No UI, nothing. I just how to create a client server architecture using C. And from that point I was hooked on. Okay, something that enables me to make what I want this fast without having to go through the whole ceremony of W file handle, etc., etc. This is what works for me, right? And then I went and I really understood how things work behind the scenes. So in those first 2 or 3 pages, the kind of programming facilities and the internal architecture that I saw, it was just mind blowing. I mean, the elegance of it under the hood was mind blowing, right? And that is what kept me hooked on to Linux through, like, in late 90s and early 2000s, running Linux was a pain, right? But once you went through that pain, you got these benefits, right? And so that's what kept me on the Linux Unix train ever since. And I've been a Linux slash Unix user. I use Mac primarily because it is a Unix, right? Otherwise, I would not use it. So, yeah, let's dive under the hood, see how things are built, not just at a command line level, but underneath in terms of what system functions are available and how all of this is put together. By the way, if you have questions about any of the slide, ask right then because I want to build up on concepts through the talk, and keep the coffee going because you're going to need it. Okay, quick mental experiment. Right? Let's say I'm in some directory, I do ls, it prints a.txt, b.txt, c.txt, then I run this command, ls greater than files.txt, then I do cat, that should be files.txt. What do you think will be the output?
Not the same. The order will be, I cannot predict.
Okay, same, but content same, order different.
No, even the content will be new line separated.
Okay, that's okay. That's just a display thing. Okay, any other answer? नहीं, so just assume that's files.txt. Anything else?
Not a eyesight test.
Okay, so the actual answer is it will. Any other answers before I reveal? The actual answer will be a.txt, b.txt, c.txt, and files.txt. Right? And now why that is, we will see why that is by looking at how things happen under the hood. So I'm going to use a few conventions in this talk. You will see these boxes in almost every slide. This I'm going to represent as what is inside the space of a process. Right? This is a running process. Like when you type ls, what is actually happening when the process is live? This is like a representation of memory plus file descriptors, etc., etc., everything together. How many of you have used C, like coded in C? Oh, quite a few. Okay. So, you know that in C we have the capital FILE struct and usually use the pointer to that, right? The actual system interface in Unix, inside that file struct is something called as a file descriptor, which is a single integer, right? And the system recognizes, for every process, the system recognizes the file using the file descriptor, which is an integer. And just like you have fopen, fclose, fread, fwrite, there are system functions underneath called open, close, read, write, which work on these file descriptors. Okay, so every file descriptor has a unique number, and you pass the file descriptor to each of these open, close, etc. functions, and it will perform the operation. So open, close, all of these are actually hooks into the actual kernel. I mean, they're not directly kernel functions, but internally they call the corresponding kernel functions. The abstraction between these calls and the corresponding kernel calls is very less, a bit of buffering, etc. only. Now, when I type ls, right, and while this process is running, you will see four, unless you give any other specialized flags like hyphen blah blah blah, if you just type ls, the process will have four file descriptors open. 0, 1, and 2 for any process is always standard input, standard output, and standard error. Right? Standard input is where you can read, it's a stream oriented file descriptor where you can read. Standard output is 1, which where you can write the output. And standard error is also something where you can write. Does anyone know why there are two outgoing file descriptors, 1 and 1 and 2? So to separate, so one reason is you might want to send output to one place but send logging errors to some other place. That is one. But there's another difference between 1 and 2. And unfortunately that, what was that list, best practices for writing programs?
Don't be shy.
No. There was some, like always do this. Well factored. No, well factored. 12 factor, right? That has destroyed the Unix ecosystem completely because it has something which says log to stdout.
Yeah, that's
It actually says it.
Two reasons. One is whatever.
Yeah.
And
Yeah.
about 12 factor.
Yeah. And people have followed that blindly and completely destroyed the composability of everything that they write. Never log to stdout, please. Two reasons. One, obviously, is you'll mix output, and so for services and all, it's okay where the output is going to go via HTTP and all. But for CLI tools or anything, don't write log to stdout. The second difference is that in the process space, file descriptor 1 is buffered. So let's say it has a 4K buffer, it will wait for 4K to accumulate and dump all of it together for efficiency reasons. File descriptor 2 is unbuffered. Right? The reason is because when the program crashes, you don't want your error logs to be lost in the buffer of the process itself. So 2 directly goes to the device. Right? It is inefficient, obviously, compared to 1 because it's unbuffered, but at least you don't lose the error messages. So these are two important reasons. The fourth file descriptor that will be open over here when you type a ls command. Anyone guess what that file descriptor will be? Okay, I've given a hint that it is something on the file system, but what on the file system? Correct, the directory file. So directory is also a file on Unix, by the way, which has a list of other files inside it. So you can, if you open, actually no, Vim has that translation layer, but you can write a C program to just dump the contents of a directory file, right? So the file descriptor for that directory, which ls is obviously going to read and iterate through, that will also be open. So now let's take a command like wc minus l, which it may have shown. This will print the number of lines coming in the standard input. That will be, the process space will be something like this. No file system required because it is reading from standard in right into standard out. Okay. Can you imagine what a similar diagram for a command like this would look like?
So there will be two boxes.
Okay.
First will be ls box, the other one will be wc, and ls output will be redirected to wc.
Yeah, something like this. Right. Just
Can you also specify what dev tty is, like why?
okay,
why is it
okay.
connected? Because
Yeah.
it's not obvious.
Yeah. So, like Chinmay said, all interfaces are file interfaces. So the terminal in which you are typing and where you are getting the output, to a process it is also represented as a file. Okay. Internally, the implementation of that file is to show things on the terminal and read from the terminal. But for a process, it's a file, right? So by default, when you're launching this command from the terminal, uh, standard input, standard output, and standard error all go to the terminal, are pointing to the terminal. And behind the scenes, like if this is a single command line on the same terminal, the terminal file is the same. Okay.
Also, like why does this even exist? Why do you have to connect? Like why can't this dev tty be something else?
As in, it can be named anything.
No. I mean, like why does 2 have to go somewhere and why does 0 have to?
Why is it connected?
Why is it connected? Why do they have to be even connected?
So in Unix, that is the standard interface for any program that you get. 0, 1, 2. I mean, you can explicitly close it, but by default, when you run it, they are always open. And if a file is open, it has to be connected to something.
Yeah, but why?
Right? Where will you? I mean, a program has to process data, right? So where will it
process data and not be connected anymore?
You can go into that mode also. So in a Unix process, you can do system calls which detach from the terminal, and then all of these stop pointing to the terminal. But by default, if you're running this from an interactive command line, that's the default that you want, that you will, the output you want to go into the terminal unless you do a redirect, like we have done for the wc command, right? If you, like just for ls, now it didn't use the standard input, but while ls was running, you could have piped something to the standard input. I've never done it. I don't know what will happen. Maybe it closes standard input. I don't know. So that nothing can.
Example,
Huh?
launch order doesn't need dev tty.
Yeah. Correct.
And provides
Correct. So that runs as what is called as a daemon process, which is detached from a terminal. Okay, and there are, I don't want to go into job and process semantics right now. Okay, but the terminal also sends signals to the process while it is, to all the processes that it is attached to. It can, and again, don't want to go into signal handling, but basically all the interactive input and output will go to terminal.
This pipe, right? So it should be also signify something. The pipe, ls pipe something. So that should be also a process, right?
No, it's this pipe.
But ideally, at some level, it should be some process.
Yeah, I'll come to how it is. But this is just a logical representation.
Just quickly, I think I'll have to double check, but the reason all interfaces have to connect somewhere is because they are synchronous and blocking.
And if there is no consumer, the program will wait, like,
No, like you can just do a empty main and it will just close without doing anything on it.
but it won't generate output anywhere else.
But you don't interact with it, it's open.
No, but it's interactive terminal is one thing. But the process has to, like, if the process is computing something, then it needs some space to dump its stuff, right?
Correct.
So it needs that sync somewhere or the other.
Yeah. Correct. So
That is that.
yeah. The preferred way of doing it in Unix is to write to standard out. But there are situations where if you are doing FFmpeg encoding,
You just write to files,
right? Over there you don't want the encoded file dumped to standard out. There's no use for it. So there it will write to a file. So not all programs have to write to standard out, but wherever possible, wherever it makes sense, which is most of the cases, prefer writing to standard out rather than opening a file and writing to that file.
Standard default.
Yeah. Okay. Any other questions? Okay. So how is this achieved? So there are, to do this, there are other functions also, which I'll get to, which actually I won't get to in this talk. You need to know 4 building blocks under the hood, or 4 functions to be able to achieve this end state. Right? So let's go through each one of them. So that command, so we said it was a fork bomb, right? So now we look at what fork is. I'm going to show some C code because that's the only way to really, that's the right abstraction to show this. If you don't know C, I'll explain what the functions do, but otherwise think of it like a typed version of JavaScript. That's in syntax, that's the closest I know. Okay. Or a version of Go which does not have memory management. Oh, that's more excellent. Okay. So this is the code. First focus only on the left hand side. Okay. So in the code you have this function called as fork, which returns an integer which is a process ID. The moment the fork call completes, it creates an exact copy of the entire process which called the fork. Okay, almost exact copy. There's only one difference between the 2 copies, and that is the return value of fork. Right? Inside the calling process, the main process, it is a non-zero value. It returns the process ID of the new process that was generated, that was created. Inside the new process, it returns 0. So once the fork finishes, if you look at the memory footprint of both the processes, there will be only one integer that is different between the two. Otherwise, they are exactly the same, including file descriptors, everything. No difference, right? And this is a very important building block number 1. Now, obviously, there has to be some difference, otherwise there's no point in both programs doing the same thing in parallel, right? You'll just have unnecessary duplicate processing. So the way you actually utilize this is immediately after a fork you will see a if else where you check the process ID. If it is non-zero, it means that you are in the parent, you continue doing whatever logic you intended to do in the parent. If it is 0, you are in the child, you continue doing whatever you intend to do in the child. Remember, the code is the same. That is something you have to understand, right? It's not like 2 different pieces of the code. It's the same code behaving as parent and child depending on the return value. Yeah.
So, I mean, there are, let's say, 50,000 instructions above it, and you call 4. When the child process comes up, is it starting at this 4th line, or is it going to invoke
This fork line, exact duplicate.
Yeah, I mean, I understand it's a process thing, but it also
Including the instruction pointer. Including the instruction pointer. Exact duplicate. If you don't do this if else, it will be exact same right through the end.
Those 2 processes run in parallel, or
Yes,
distinctly?
they'll be in parallel. Which interestingly, I'll just go back here. If you run this command on DOS, you won't get this. It will spawn one process, it will take the output, store it in some temporary file, then spawn the other process, take the output. It's not going to run in parallel. But whereas on Unix systems, it runs in parallel. I don't know whether new Windows even ships with the DOS anymore. But okay.
Take for address space will be as well, like they have different memory access, right?
Logically, it's a different address space. So changing something in this address space won't impact in the other address space. They're two different processes now.
They can run in parallel because
Yeah.
otherwise they can't.
Yeah.
Clobber each other.
Yeah. It's two different processes completely. Okay, should I go ahead?
But it is more happening in the previous example. You said that things will run parallel.
Here. So I'm showing how we get to this end state using all these mechanisms.
There is
So,
a fork happening here.
there is.
Parallel here.
There is a fork happening. To get to this state, you have to fork. The only way in Unix to create a new process is to fork. There's no equivalent of spawn.
There LS will be a process and WC will be a process.
Yeah.
They'll be communicating via the pipe.
Okay, any other questions? Ask your questions, because if you don't get this, it's going to be difficult more and more. It gets hairier and hairier.
So you said with the LS pipe WC, it will create these two processes. But logically, shouldn't it be blocking, because LS wants to list all the files and word count has to then go and look into those files.
But why should that be blocking? LS can continue and both can.
I'm also thinking this way, that fork has to create exact same copy of the process, but these are two different distinct processes.
Yeah, I'll get there. This is the end state. I'm just covering step 1, step 0 in fact.
If the processes after a moment after forking, if they are exact replicas of each other, then that's too much waste of memory. Is there a way to remove the previous instruction? Because I know, for example, to remove the parent process instructions, because I no longer need that in the child process.
But the OS doesn't know that you don't need them. As a OS cannot make assumptions on your behalf as a program, so it just replicates.
So they remain there.
They remain there. You can free them in the child.
Okay.
Right? If you have dynamically allocated, you can free them in the child if you don't need it.
So if I get a stack pointer from before 4, PID के ऊपर मैं and so somehow I added something, the stack pointer where the second 4 जो होगा right. So I replace that space or some integer value +1 or +1. So in that case also it will work from the same PID, the second process, child process, or it will be in from different thing, or segment pointer आ जाएगा.
So after the fork, these two are independent processes. They have independent logical memory. So
with the garbage in that thing, if I try to do a mischief with this kind of code, so I get the stack pointer, जहाँ पे the line number if is there, like PID is there, and I somehow try to manipulate it with the existing value.
it will manipulate in that process.
Okay.
So if you do it in child, it will do it for the child. If you do it in parent, it will do it for the parent. If you do it in common code, it will do it in both, separately, independently.
The logical address space of both processes is exactly the same.
Okay. So offset will change. So offset will basically take care of the.
No, even the offset will be same. So what you see for the logical address space that you see as a programmer does not map to the same memory underneath. Like the OS uses page tables to actually map it to different memory, but the abstraction you see is the same address space.
Was the reason why I'm telling that I was just doing something where I was trying to skip one line after a function call.
Skip. Oh, okay.
Okay. So in that case, what I have done is that when you do a function call, so it get a stack somewhere. So when you return from that function, if you manipulate the return address, so you will jump to other number of lines. Like So I'm
In the function, you are manipulating the return address.
So when in the function, what I'm doing, I'm getting the star pointer of that function. And then if you go one step behind, if you subtract -4, depending on the address thing, then you will get a space where you can actually manipulate the value of that. So it is return address where you need to go after the function is finished. So if you are forking something, so is that applicable over here also? So there will be separate two processes.
So whatever you do in each process will affect that process independently. You can't, so there's, in one process you cannot do anything that will change the other process. I'm more curious how you got the stack pointer in C, but that's a different
It's a go-to easy.
Yeah, so my task, so there was one problem.
Wait, later, there's too much after this thing.
Just something, so fork is not a function call, it is basically something else.
Yes, so that's the point.
So there are a set of function calls exposed to you by the standard library on any Unix, the C standard library, which are actually calls into the corresponding kernel functions. So they invoke the kernel functions, and there's a very thin layer of abstraction in the standard C library. So this fork, so all these calls that I'm showing, they are hooks into kernel function, and the kernel is actually doing the work for you. It's not a standard, it's a different function. So these are called system calls. So if you look up Unix system calls, you'll get a list of all of these. Any other questions?
And isn't so printf is also similarly?
No, printf is all user space. Printf internally might call the write system call. Actually it doesn't, it calls fwrite, and if the buffer is full, fwrite will call write with all the data. The write is the system call level. Okay. Okay. Next building block is called pipe. Okay. So you create an array of 2 integers. Okay. You pass it to a function called pipe. Again, this is a system call. Internally, a pipe is created in the kernel which connects these 2 file descriptors that are written. The first file descriptor is the read file descriptor, the second file descriptor is the write file descriptor. Anything you write into the second file descriptor will pop up. If you read, it will show up in the first file descriptor. Right? Internally, it goes through a FIFO buffer inside the kernel. Okay, you might think, what's the whole point of this? You can just keep a buffer in memory, but we'll see how this is useful. Okay.
So this is the way to, this is a it's an API that C provides to connect to file descriptors.
To work on file descriptors and even create new file descriptors. Like the open call, open function will return a new file descriptor. Close will close the existing file descriptor.
And this pipe function is what is getting called when we put a path.
Yes.
One of the functions. Yeah.
Buffer space is outside the program.
It's inside kernel space. Here, clear? Okay. Next building block is called dupe, or dupe 2 specifically. There's a variant called dupe which is not useful for our purpose. What dupe 2 does is that, so what the first argument that you give to it, it makes the second argument, the file descriptor of the second argument, an alias of the first one. And if the second one is open, it closes it and makes it point to the first one. So here, if I say dupe 9, 1, it is, so earlier 1 was pointing to dev tty, it will start pointing to 8 because it's an alias of 9. If you put anything in 9, it pops up in 8. If you put anything in 1, it pops up in 8. Both, you can use them as identical file descriptors. Okay, again, internally what it is doing is both are attached to the right end of the pipe in the kernel. So anything you write in 1 is going to go into the right end of the pipe, come out of the other end. Okay, clear? Okay. Now let's look at pipe and fork together. So earlier we just saw pipe, direct one-to-one connection, but there is a subway underneath, right, to cross the road. now if I create a pipe and then I fork, right? Now remember the fork semantics, everything remains identical, right? Including all the file descriptors, including pipe, everything. So what you essentially get is, if you write to 9, it is going to go into the right end, it is going to go into the read end, and now there are two read ends and there are two write ends. Okay, and all combinations will work at this point if you utilize them accordingly. Anything you write into 9 can be read at 8 in both processes, because the underneath piping is the same. Of course, the data is not duplicated, so if you read from 8 in one process, it won't be available to 8 in the other process, it will read the next data, right? It's a single FIFO buffer. Okay, but the ends are available for reading. Clear? Yes, it's a buffer, yeah.
And when you say everything gets duplicated, the kernel part does not get duplicated.
This doesn't get duplicated. Only the interfaces to the pipe get duplicated.
Even binary you said gets duplicated, but not the kernel.
User space memory gets duplicated, kernel stays the same.
2 was not buffered, right? You mentioned.
2 was not buffered.
So at this point, if anyone writes to 2, that data is lost.
No, it will go to dev TTY. So
Yeah.
2 is still pointing to dev TTY.
Yeah, in this case, but if 2 was also connected somewhere like this, then unless someone reads it,
Yeah, it's
the
lost.
data will be lost.
Correct.
And you can redirect stderr to the pipe also. There is a way to do that. So you consolidate both outputs, and then you'll get this synchronized, buffered, synchronized blocking behavior.
Can you just pass that bottle, white bottle?
There are reasons you might want to do that.
Okay. This is again important slide to get the hang of, because now a lot more things are going to come together after this. Okay, should I go ahead? Okay, now let's look at what the shell actually does. We'll build up on what we have seen so far. So first, and this is for the pipeline that I showed, right? ls pipe to wc minus l redirect to whatever. So first it is created the pipe, it has forked, right? After the fork in the parent, right now focus only on the parent part, ignore the child part over here, okay? In the parent, it is going to call dupe2 on the right end of the pipe and standard out. So now standard out starts behaving as the right end of the pipe. Anything that you put into this file descriptor 1 is going to come out either in 8 or in this 8, depending on what order who reads. Okay, but it's available in both processes. It's going to go in this under this subway tunnel. Okay, clear so far?
How did you create it?
Pipe. So I'm assuming that this pipe FD2, when pipe returned, it was 8 and 9. I had to give some numbers. Could be 100, 101 for I. Okay. Next step that it does is it is going to close off 8 and 9. Not needed. Now when you close off 8 and 9, what you end up with is this. Okay. 1 is still pointing to the buffer. So when you close a file descriptor, so unless the file count to the actual underlying file goes to 0, the file isn't really closed. You just got rid of the file descriptor. Okay, so this is part 1 of how the output of 1 is now sending data somewhere into the second process.
Okay, so you achieved this by first creating the files, and
Then fork,
after the fork, you
duplicate.
you duplicate it, and you told one of the processes to ignore that. Close that.
So we are right now looking at this code over here. So if you are because you are in the parent.
Yeah.
If you are in the child, it will go into this code here, which we have not seen yet.
So you have handed over the pipe to child.
Fork automatically does that. Fork will create, so
I mean, fork gives to both, but by closing, you have given them away to child.
I have not given them away, I have just closed it in the parent. Child always had them.
Yeah, right.
Both had them, now parent.
Both had them.
Yeah, both had them.
Now in parent I have given them away.
Child doesn't know that parent has closed the.
Child has no idea what is happening in the parent right now.
They are uncoordinated that way. The pipe is the way.
Both are happening in parallel, but I have to tell you in sequence. Okay, clear so far? Now let's look at what the child does. By the way, I am keeping the code listing the same in both because it is the same code that is being executed. Right? It's just that they are going in different branches of if because this PID value is different. Okay. Now in the child process, it does the same thing. It dupes 8 to 0. So 0 becomes an alias of 8. So anything that you put in 9 will pop up in 8, or it will pop up in 0. You can read from both places. Anything that you put in 1 over here will also pop up in 8 or pop up in 0. Okay. Repeat the same thing.
So when you say pop up in 0 means
If you read from it.
reading from 0.
When you read. When you read, it will show up in 0 or 8, depending on where you read it from. Then again you close these two file descriptors in the child, and this is what you get at the end. So now we have a situation where the standard output of the first process is now piped to the standard input of the second. This is what the shell does when you press that single pipe character. All these operations in sequence. Here I have obviously done a hard-coded version. The shell first parses the pipeline and
Here the shell 1 is the LS, shell 2 is the W.
not yet. Right now, shell 1 and shell 2 are both forks of shell process itself, the sh process. So you have a top level sh process where you wrote the command, and then it spawned sh1 which spawned sh2.
At this point, I think we have a microservice architecture where we have a Kafka in the middle of two processes. I mean, it literally is. It really is that.
Without the Byzantine network in the middle.
Because you have shared memory.
Yeah.
It literally is that.
Okay. Now let's look at how redirection will happen. So this is the full command line. We have just seen ls pipe to wc, what will happen, right? But the shell also sees a greater than something for the second process, for sh2. Right? Any idea what it will do after this? So first it is going to open this file, right? Any guesses what it will do next?
It will do a
Loop 2 and
so loop 2 to connect the output to the file system.
correct, because it's a redirection. You want to redirect 1 to the file, so you loop 2 6 into 1, both point to the same thing, and then you close off 6. No longer required.
Because you cannot do this directly.
As in?
As you can't be just do one pointing to file.
No, it has been set up with one pointing to this thing. Right? That's the standard interface.
I think the issue is like when you open that file count.txt, you will get 6.
Yeah, you will get 6. You will not get 1. Thankfully. Otherwise, anytime you open a file, your standard output will be lost. Cool? So now we are very close to the end state that we have. Okay. Now comes the last part, last building block, which are the exec calls. What the exec call does is that it replaces your current process space with the process space of a new program starting from scratch. File descriptors, etc., everything remains the same. Just the process space, the code, and when I say code, not the C code, the binary executable code, that gets pulled into memory and replaced. So this shell 1 process, when I do exec v call of ls, becomes ls. This shell 2 process becomes wc, and the end state looks like this. The entire process is going to be replaced, and it is going to, both programs will start running from scratch, from the start, which is in C terms the first line of the main function.
So this means if your shell has a footprint of 100 MB, let's say, and you write a pipeline of 10 pipelines like ls pipe, wc pipe, something, then the moment you execute that pipeline, your footprint becomes 1 GB, like 100 MB instances of 10 shells.
I'll come to that. I'll come to that in the end once. There's an optimization in the kernel to not let that happen.
Okay.
It's called copy on write, which means that it actually creates new memory. So okay, in logical address space, yes, logical memory will increase, but actual memory consumption doesn't increase because after you fork, the kernel only creates a real copy if you modify the memory. Till then, it keeps the same copy. So it's called copy on write.
They had to do this because there was no memory to speak of when Unix was written in 1970.
Is the same copy on write as
I mean, copy on write as a concept is the same, but the ideas are very different. Okay, and this is the end state that we reached that we wanted when you run a pipeline like this.
But the kernel buffer is still in the middle. ते अजूनही आहे.
So I've replaced the kernel buffer with a orange line. So anytime there is a command line running with a pipe, for every pipe you should know that there is a kernel buffer underneath to pipe data. Any questions? Cool. So in effect, this is the entire code listing sort of. It's more generic if you look up the shell. So if you look at some of the, like probably the first version of the shell on Unix, it's really small, the code, because there weren't a lot of facilities. So this kind of code stands out more prominently. Right? Here, obviously, I've hard-coded ls and wc and all that, but those get filled in dynamically by parsing the command line. And also the number of such forks and all also happen dynamically. So I've given a static version of what happens. Yeah, that's pretty much it. If you want to really explore more, I suggest these two books, Design of the Unix Operating System. The first one is, it doesn't have a lot of C code. It's more conceptual about architectures, and it also goes into the architecture of the file system, like how inodes and why you don't need to defragment on Unix and all of those things. The mounting concept, that you can just take one file system and mount it anywhere in the hierarchy that you want of another file system. So how all that happens under the hood is covered over here, plus process space, terminal interaction, all of it. The second one is like a complete coding book. It will go in details of all the system calls that we just saw and more. Right? It also it has chapters on network programming a bit, but it's really a deep dive into the system call level and how different system calls work. Cool, thanks. That's all from me. Any questions that I had said will
Talk about plan 9 also, no? Because last time.
well, last 9 is nothing related to plan 9. Uh, so if you look at how Unix evolved, it didn't stick exactly to the Unix philosophy in terms of files. Everything is a file and some other concepts. So sometime around what 95-ish, around 95, there was another project at Bell Labs, AT&T Bell Labs. I think it was forked off into a separate company by then. It wasn't part of AT&T, where they started building an operating system which which started from Unix, but they wanted to go the full distance in terms of abstraction. So in that operating system, you will have things like even network sockets have file IO interface. CPUs have a file interface. So you can do stuff like mount a CPU of some machine across the network onto your machine and use that, right? So they basically took, and a lot of they wrote their own dialect of C to work with that, which was a bit different. Uh, that dialect of C is actually the predecessor to Go language. And I had tried running Plan 9 in QEMU back then. I mean, successfully I did it. But in terms of practical use, it's more like an academic operating system. If you want to see the concepts, it's quite interesting. But I think the lack of device drivers and community support around it caused it not to sort of take off in the commercial world or the professional world. But yeah, that's an interesting sort of segue of the Unix operating system that you can look at.
Like it's a true distributed system, like network transparent, everything. Like you can have your laptop and you don't care where the computer is in the world.
Yeah.
Like it's true distribution because it's got a global namespacing scheme. Like it did a lot of things that Unix didn't completely do.
By the way, a lot of the concepts were then incorporated into Linux. The concept of namespaces,
Yeah.
for example, that came from Plan 9.
Namespaces, Union file systems,
Yeah.
network lock devices.
Yeah. I have a friend of mine whose daily driver is Plan 9. So he runs Linux under Plan 9 and like he just works. WSL runs Plan 9.
Oh.
WSL's initial process plan.
No, that may be something else.
I don't know, file system.
Yeah.
I
So,
just felt the name familiar and verified.
by the way, you can use parts of Plan 9 independently in Linux. Like 9p is the file
Yeah.
system. You can just use 9p as the file system. Then I forgot all the other parts. But yeah.
This guy wrote G9 Git's implementation for Plan 9.
Oh.
Very
Uh, there were some questions which I said I'll take at the end.
You're right.
Copy on write I covered. Any questions in copy on write? Okay. Anything else? Okay, cool. Thank you. Okay.